Good evening, guys. I am Prashant. I co-present this talk along with Daniel. We are from CERN. For the next 25-30 minutes, we talk about our attempt to detect anomalies in our database infrastructure using Apache Spark and Spark streaming. As some of you are not, okay, this is the general outline of the talk. So a few slides to tell you what exactly happens at CERN, usage of Apache Spark at CERN, and challenges faced while building the data lake. So this is a step before you can try to do cool things like machine learning or correlations. And then we move on to detecting anomalous connections to our databases, and then some intelligence into monitoring. CERN is a European laboratory for particle physics. It was formed in post-war Europe to do fundamental physics research. Today, it is a worldwide collaboration, so there are countries from Asia, America. So there are around 10,000 people who use facilities that are at CERN to do the research. These are people from the research institutes across the world. So there are around 2,300 people who run the show, and CERN has around $1 billion to play with. So what exactly we do, we try to answer some of these basic fundamental questions. So why do particles have mass, and why there is no antimatter left in the universe? How exactly we answer these questions? So CERN built a large Hadron Collider beneath France-Switzerland border near Geneva. This is 27 kilometers in circumference, 150 meters below ground. Where the protons are accelerated at the speed of light, and they collide, and the collisions are observed, and the data is taken and analyzed. It's the emptiest place. Obviously, you don't want to have any noise, so its vacuum is taken out. And it's the hottest planet in the galaxy, so we use a lot of helium to cool it down. Coming to Apache Spark at CERN, so nowadays the adoption is increasing, and it's becoming a popular general purpose compute engine, both for analytics as well as ETL. So everybody starts using Spark for ETL, and then it looks good and nice and clean API, they move on to analytics as well. So we mainly use it on Yarn today, but it could change now that we have seen in the keynote that there is an integration of Apache Spark with Kubernetes. So the adoption is growing, as I said. So the accelerator you have seen, like in the previous slides, the logging data that is spitted out of this accelerator will be analyzed in future with Apache Spark as well. So the whole IT infrastructure at CERN is monitored using Apache Spark streaming and Apache Spark. And then there are initial studies going on to analyze high energy physics data, which is, let's say, in CERN developed format. So now coming to detection of anomalies in database infrastructure. So our motivation for this work is essentially to detect anomalies. So for example, if you have your CFO connecting from let's say China on Saturday evening, this could be an anomaly, or he was actually there and trying to connect your critical database infrastructures. That is the motivation for this work. So we run a large database infrastructure, relational database infrastructure as well. So the metrics and the logs are collected from these databases and sent to a central store, and where we perform the analysis. As you can see on this picture, so we have around roughly 500 relational databases. Now we also have InfluxDB that is in the mix. So the first step towards our end goal was to build a data lake. So the objective here was to centralize the logging metrics information into a streaming format for offline analytics and real-time analytics. With the goal of solving these use cases, like detecting anomalies, whether it is in database connections or in the workloads or in the resource usage patterns, obviously for troubleshooting and also for capacity planning. So we want to collect diverse data. So the data we want to collect is diverse. Some of this data is in the database tables, and some of the data is in the log files. What we have done is we have a Flume agent that runs on each of our database machine. For the data that is in the tables, we have developed in-house JDBC source for Flume, which collects the data and writes out into Kafka. So you will see the architecture diagram in the next slide. For the log files, we use out-of-the-box tail source that comes with Flume. At a high level, it looks like this. So the Flume agent takes the data that we want and puts into Kafka. And then we also send it into HDFS and also to Elasticsearch. And also in the middle where the Spark streaming comes into picture, which hooks into the topics that we want and does the real-time analysis here. So once you have information in a data lake, some of the problems are easily solved. So you could use like Grafana, Kibana to do your aggregations, slicing, dicing, and also do your dashboards. As you can see, like some of the failed logins we see to the databases are appearing here. But we want to do more than this. So if we want to basically, as I said, detect anomalous database connections. So our first approach was to use a KNN classifier. As you heard in the morning keynote as well, is K nearest neighbors is a common classifier that is used in anomaly detection in other cases. So we want to classify a connection as either normal or anomalous. Usually, from our experience and also looking at the literature, anomaly detection suffers from high false positive rate. So that is, you classify something as anomalous even though it is not. So you have to choose your features such a way that they represent the user connection patterns. So the data we have here is in the JSON format. So we have the information from where the connection is coming, the machine, the username, and the time, and we also have some more information based on the database type. If it's let's say Oracle, you have a service name that is being connected to. So from this we do typically if you're doing machine learning, you have something called feature engineering. So you extract and transform your features. So these are the features we have selected for our KNN classifier. So there is a host name which tells from where the connection is coming, at what time, and which program, whether it is like Python or something else. And the timestamps, we don't want to take the timestamp as it is, but we are taking hour of the day and day of the week features. So for some of these features, we want like in a numeric format, right? So we use a string indexer to do the encoding into like the vector space. And essentially, if you have too many features, Spark.ml also provides APIs for dimensionality reduction and principal component analysis. Where if you have too many features in the vector space, it's better to reduce for you to have a better outcome. So this is how our let's say the KNN implementation works. So we run it, let's say, in our test system for a couple of weeks. So whatever comes during these 2 weeks, we tag it as normal. So that's our training data, because we don't really know what are the anomalies, right? And then a new connection comes in. Then we compute the distance from this point to the existing points in the vector space. And as I said, you need a metric to compute distance. So in our case, it is a weighted sum. You could also use like something else. So we also try to use a Euclidean distance and Manhattan distance. But in the end, we have narrowed down on the weighted sum. So once you have all the distances, so you find the nearest neighbors. So in our case, k is 1, because we want to find the minimum distance. And then if this minimum distance is less than our threshold, it's normal. Otherwise, it's anomalous. So if you have a data point that is outside like this, and then, the distance is greater than threshold, so you tag it as anomalous. So this is this is more interesting to do with Spark streaming because you can actually divide the vector space by user. So you don't need to compute your distances for all the training data you have. So you only compute to the past connections from this particular user. So this makes a good use case with Apache Spark streaming to scale out and essentially classify something as anomalous or not. So in the next slide, I have put the distance function we use. So we try to classify around 10 million database connections per day. It's not a very enormous workload, so we only run it with 6 executors, each with 4 cores and 8 GB of memory. And to tell you something about efficiency of our classifier, it's around 80%. So this is not a very easy job that, so you do something like this and all of a sudden you have very less false positive rate. So we are trying to also play with the distance function and see, what fits best. So next, I hand over to Daniel, who talks about our general purpose metrics monitor.
Hello, everyone. Well, we have seen how we can detect anomalies on database connections, but we are not only collecting database connections, and we want to detect anomalies also on metrics. We collect many metrics from each of our database instances, and we would like to know if these metrics are behaving anormally. So for this, we have developed a general purpose metric monitor, and we have based our implementation in Apache Spark. I would like to introduce to you the monitor that we have developed, which is open source as any other thing that we develop in the organization. So first, here you can see the data flow, so you can declare different metric sources for your job. And then they will be ingested and processed by different monitors. Monitors are basically ways of declaring what you want, at which metrics you want to look at, how you want to analyze them, and when to raise notifications. All the incoming metrics can be from the incoming metrics you can generate new metrics, which this is a key part of the monitor, because you can aggregate them. For example, you could aggregate metrics coming from different systems, in this case from different sources, and you can apply mathematical operations to this. But not only that, you can also aggregate them in time. So you could calculate, for example, the average during the last 5 minutes, or the minimum value, or the difference. As we will see in the next slide, you can apply different operations. I will go through each of these components and explain how they work. But before this, I would like to mention that many of these parts and these components are can be easily replaced, or you could easily implement a new one. So you can easily implement a new metric source. Right now we have one in Kafka. You could write yours that consume from an API or consume from Elastic. Then you have a pre-analysis. That is a way to, let's say, massage the value of your incoming metrics. It can be also easily replaced, and you could implement a new one. Then you have the analysis. Well, I will explain this in detail. And then you have also a property source, because the configuration of the job can be updated while running. So you can change the number of the monitors that you have and what each of them does. And then the results of your analysis can be sent to an external source to see what the analysis is doing. And the notifications can be also sent to an external source. You could send these notifications to Elastic, or you can send them to a sink which send emails or triggers some actions. So first of all, what is a filter? A filter is basically the way that we say to which metric this monitor should analyze. For example, as I wrote here CPU usage of all databases, or all the databases in productions, or only database MySQL databases. So here, basically, our metrics has attributes, and we filter by these attributes. You could also apply regex expressions. So there, each of these monitors could look at many metrics, not only one. Then you have pre-analysis. Pre-analysis is something that you used to do before performing the analysis of a metric. A pre-analysis could be, as I saw here, simply the average over the last 5 minutes of a metric. Here you can see that this pre-analysis probably doesn't represent very well the average value of the incoming metric, because it's doing some drops that are not you would like to get rid of it. So we have implemented a different pre-analysis, which is a weighted pre-analysis where the latest value has a higher weight than the older one, and it better represents the value of your metric. Another pre-analysis could be the difference with the previous value. So here the line at the top represents the real value, and the pre-analysis create basically the difference with the previous value. So you can detect easily some drops. For example, later applying a simple threshold, you can detect if in your metric some big drop occur either down or up. Then once you apply the pre-analysis, you apply the analysis. If a pre-analysis were applied, it will work over the value that the pre-analysis produce. What is the analysis? The analysis basically answers the following question. What is the status of the metric? The status of the metric could be okay, could be warning, or could be error. So we are saying that okay if the metric is behaving as expected, warning if it's doing something strange, and error if it's doing something that was not expected at all. Exception if the processing it has failed for something, if the metric is missing, or any exceptional circumstances. Some pre-analysis that we have implemented: a simple threshold. You declare your threshold, and if the metric goes farther than this threshold, the status will be warning or error. The status, you can see it, can be seen at the top of the graph. So when the metric is going upper, that the orange line, the status is orange, and when it's going upper, that the red line is going to error. But this is quite simple, as you can imagine, and you need to configure these thresholds. We can do something a bit more complex, something that we call recent analysis. This is basically calculating the average of the value for the last 10 minutes, 20 minutes, a period that you configure, and is also calculating the variance. And out of these two values is automatically calculating this threshold. When the value of the metric is going out of these thresholds, the status produced by the analysis changes. This is using the same pre-analysis, recent pre-analysis, but as you can see, the thresholds are easily affected by any outliers. So we develop another analysis, which is one working with percentiles. If you don't remember what's that, but it's basically using a percentage of your data. So you could configure this analysis saying that you want to use 98% of your data, and then this threshold will use only, let's say, the 98 more normal values of the historical data that you have received. But you can do something more complicated. Well, and this analysis is what I'm showing is what we have implemented, but you could implement your own. Here, I'm introducing one that is seasonal analysis. This seasonal analysis is applied when you expect your metric to do the same during a season. A season could be an hour, a season could be a day, a season could be a week. Imagine that your metric is doing every hour the same, as you can see here. If we expect this, we basically say that the analysis is seasonal and the season is 1 hour. We apply some pre-analysis to this value, to this metric. We calculate a simple average. And then what the analysis does is calculate some thresholds out of this value. So here what you can see is the warning and the error thresholds. If the metric goes out of these thresholds, error or warning are created. All right, this analysis could work nicely, but we don't want to get notifications every time that we get a warning or an error. So we want to put a bit more intelligence on this, and then there is another component that you declare in the monitor, and is the notificator. Notificator is basically the logic that you follow to trigger notifications. When a notification should be triggered is based on the status of the analysis. So it's based if the metric has been in error, in warning, or okay, or exception. For example, we have one that is one notificator that we call constant. So if a metric has been in error for the last 10 minutes, we get a notification, for example. This is the case. This is, of course, configurable in which status you are expecting the metric to be and for how long you would expect it to be like that. But sometimes the metric is behaving strange, but it goes back to okay, but it goes back to error. So you could implement a different notificator, which is based in a percentage. So if the metric has been, so you basically configure a percentage. In this case, it was configured 80%. If 80% of the period that you configure, for example, the last 40 minutes, the metric has been in error or in warning, notify me. And this is the case. During the last 40 minutes, the metric has been in error or warning. So basically what I was explaining is for configuring such thing, this is the configuration file where you configure the metric source, the result sync, and notification sync. And then you have monitors. This configuration could come from an external source as well, so from an API where you can update this configuration at any time, even when the job is running. And then also these monitors can detect when a metric is missing. So you wouldn't get notified if the metric is not coming anymore. What we are doing right now with this, we are monitoring around 30,000 metrics per minute. And this is done on 3 executors on Yarn. And it's taking more or less half of processing time. So every batch, every minute is taking 30 seconds of processing time. As I mentioned, this is open source, can be used by anyone. And here is, on GitHub is the code where you can report any issue or collaborate with the project. From this journey, we have learned some things, and I would like to share some thoughts and tips that you may find useful. The first one, something that you may use when you are playing with Spark Streaming, is time. When you play with time, most likely, or at least me, end up playing with milliseconds, seconds, resting, adding, and this is kind of messy when you apply also time zones and all this. But Java 8 comes with a very nice API. Basically it's in Java time, that replaces date, the date that we all know, by instant, and then you have also duration that you can remove from instance. Instance basically represent an instance of the time, as they did before in Java 7. So if you are playing with time, in case you are using Spark Stream, it's quite likely. I encourage you to try because it's quite readable and nicely, and you forget about milliseconds and converting on other units. Another tip that also brings Java 8 the possibility of playing with lambdas, streams, reference methods, and this plus extending RDDs. For me, it has made the code quite clear. Here you can see the main logic of the job that I just described, and how I go through the different data sources, and I create metrics, and then I generate the new metrics that I define. And then I analyze with the different monitors and I create results. And then if the sync is present, I sync the results. This code for me is quite readable, at least a way more than the one that I had before. So, and just by using Java 8 lambdas and extending the streaming from Java Spark. Another tip that creates more than one headache to me is Spark checkpointing. When you use Spark checkpointing and you are developing, you are early developing something, you are continuously losing your data because your data pipeline changes, and then the data that you checkpointed is not valid anymore. You delete it. And then, even worse, if you have this running in production, and then you release a new version of your Spark job, and then you have to remove all your historical data because you create a different pipeline, and then your checkpoint data is not valid anymore. Well, for this, we have just implemented our own load and save mechanism in the case we use map with state. That is basically the mechanism where how we keep a state of stateful operations. As conclusion, building the data lake it has been a great idea for us in order to use our data either for offline analytics and online analytics. The implementation of anomalous connections has helped us quite a bit with the detection of anomalous intrusions in our databases. And then with the intelligent monitoring tool is nice that you don't need to care about configuring it, setting your threshold for your metrics, as long as this is learning by itself the thresholds, and you need to configure very little. And as you remember, this is open source and it can be used by anyone. And for sure, Apache Spark, it has helped us to abstract big part of the logic and remove many hours of working on a streaming platform that would have been quite harder to develop with such framework. And that's it from our side. If you have any question, I'm open to answer them.
Yeah, we probably have time for one question. Who is the lucky person?
In your k nearest neighbors model, you had some sort of distance function with weights.
Yep.
Where did you get the weights from? Or how did
Well,
you
the weight is basically something that we are experimenting from. We started without weight. However, the implementation was done from scratch with weight, and we are basically trying to adjust them manually in order to get better results. Yeah. Guesswork.
All right. Any other questions? Apparently we have one more minute.
Did you consider commercial monitoring tools at all, rather than building your own from scratch here?
Well, since our organization is let's say, found it, but let's say we prefer open source solutions or using open source frameworks to develop our own tools to perform such task. We prefer to avoid commercial solutions. Sorry? Yeah. Well, sometimes it's not that easy.
All right, that's all time we have for this talk.